Hello everyone, welcome to lecture 15 of the online course on modern display technologies, flat panel display. In today's lecture, we will be covering polarization states of light, and then we will discuss about the propagation of light in anisotropic optical media. So here is the detailed outline of this lecture. So in the polarization states of monochromatic waves, we will discuss about the linear polarization states, circular and elliptical polarization. We will discuss about the polarization ellipse and the principal axis, also the ellipticity of elliptical polarization. Then we will move on to the discussion of propagation of light in anisotropic optical media, where we will briefly revisit the Maxwell's equation. We will discuss about the eigenmodes, wave vector and operator substitution. We will see the eigenvalue equation in its matrix form. We will talk about the variable substitution, Fresnel equation of wave normals. Then we will also discuss the eigen electric field vector and the refractive index ellipsoid, or simply called as index ellipsoid. So let us first discuss polarization states of monochromatic light. Now, what is this polarization? It is basically related to the electric field of light. So when a monochromatic plane wave or plane light wave propagates in a homogeneous isotropic medium, you only require electric field to characterize it, okay, because all other properties can be calculated from this electric field only. So if you know about E in a homogeneous isotropic medium, you can calculate D, H, B, everything can be calculated from this E. So what is the general form of this plane wave? We have earlier seen the wave equation, and this is the form in which you can assume the electric field to be in, so that that particular wave equation is satisfied. E equals A e to the power I omega t minus k dot r. Okay. Here you can see A is a constant vector. Okay. So you are basically looking at the amplitude here. Now e to the power I theta, using Euler's formula, you can write it as cos theta plus I sin theta. So here the real part is basically representing the actual electric field. Okay. So this kind of representation is called analytic representation. Now one important parameter to look here is that this is term shows the time dependency, and this one shows the with distance how it changes. So this is where the spatial parameters will get in. So when you talk about the polarization state, it is basically specified by the electric field vector. So in a liquid crystal device, studying of this polarization state of light becomes very important, because liquid crystal can be used to manipulate the polarization state of light, and you can consider the field to be propagating along the z axis. In that case, the real electric field will have two components, either along x and y. So you can basically assume Ax as the component along x axis, Ay will be the component of the real electric field along y axis, and you can take the ratio of Ay by Ax, that is called the amplitude ratio. So this is an important parameter to specify polarization of light. The other parameter is delta, that is the phase difference between these two components of x and y. Okay. So with this you can actually specify which polarization this particular plane wave is referring to. So, if you see the algebraic form of the x component, it is Ex equals Ax cos omega t minus kz plus delta x. Similarly, you can write the y component as Ey, which is Ay cos omega t minus kz plus delta y. So, what do we see here? Ax and Ay are basically the amplitude, they are basically the positive numbers. Okay. Delta x and delta y are basically the phases where each phase lies between minus pi to plus pi. So, how do we calculate the phase difference? It can be calculated as delta y minus delta x, and you know that this phase difference will also be within the range of minus pi and plus pi. Okay. So, what is the key concept here? That means if you consider a plane wave to be propagating along z direction, it will have electric field oscillating in the xy plane. So, you can actually get the component of the electric field in the x direction or x axis, along the x axis, along the y axis you can call it as Ay. You can take the ratio of Ax and Ay, so that is the amplitude ratio, is very important to determine the shape. Okay. And then you can also calculate the phase difference delta, which is delta y minus delta x. So, that basically determines the type of polarization. So, what are the special cases that people use in day to day life? When delta equals 0 or pi, it is basically linear polarization. When you have delta coming out to be plus minus pi by 2 or plus minus 90 degree and the amplitude ratio is 1, that is Ax equals Ay, you get circular polarization. Otherwise, you will get elliptical polarization. So, let us see how it looks like. So, this is a beautiful illustration of a light that is linearly polarized and propagating along z direction. So, what you see here, the blue one shows the electric field vibration along the x-axis, and a red one shows the vibration of the electric field along the y-axis. So, actually you can see the resultant electric field vector basically depends on these two, okay, just by doing the vector summation. So, it will be somewhere along this xy plane. Once again, what is the condition for linear polarization? The phase difference between these two components, x and y component, should be 0 or pi. So, the polarization angle, so when you have 0, that means electric field vibrate along a line at angle plus phi, okay, and you have tan phi, which is equal to Ay by Ax. When you have the phase difference to be equal to pi, that means the electric field is basically having an angle of minus phi, where you can get this phi from this. So, here tan phi will be minus Ay by Ax, but in both cases the electric field vector basically traces a straight line in the xy plane. So, if you want to get a spatial view of this plane polarized light, okay, so you can consider at any instance of time, say time t equals 0. So, here you can see at t equals 0, what is that curve? This electric field is basically tracing on this xy plane. So, you see that it is basically tracing a straight line, okay, and it is on a plane. So, you call it as a plane polarized light. So, linearly polarized light or plane polarized light. However, when you see circular polarization states, there what happens, the two amplitudes Ax and Ay are same, but the phase difference between these two will be now pi by 2 or plus 90 degree. Okay. It can be also minus 90 degree. Okay. So, what happens in this case, you can write Ex as A cos omega t minus kz, and Ey will become A cos omega t minus kz plus pi by 2. So, this can be written as minus A sin omega t minus kz, right. So, here you can see the equivalent electric field vector is basically tracing a circle on this xy plane, okay, and it is rotating in the clockwise direction, okay, when the observer is facing the wave, okay. So, you can basically tell that this is a right hand circular polarization, right. So, you can see this at z equals 0, okay. When you put z equals 0 in these two equations, you get Ex equals a cos theta cos omega t, Ey equals minus a sin omega t, okay. And what you see, the electric field vector is tracing a circle, okay, and at any fixed time it is basically a right handed helix in the space. When the phase difference is minus pi by 2, you can see that this is basically going in the counterclockwise direction. However, the amplitude relation is here also same, Ax to be equal to Ay, which can be A, okay. Only difference is that the phase difference between y and x is here minus pi by 2. Now, elliptical polarization case is a generalized form of that circular polarization, where the two amplitudes are not equal and the phase is also, the phase difference is also non-zero, okay, and it is not even pi. So, this is the general case when you consider Ax is not equal to Ay and delta is not equal to 0 or pi, okay. So, what you get is something like a elliptical polarization. So, you have to understand that both linear and circular polarization can be considered as special case of elliptical polarization, because in this elliptical polarization, in the linear one you can have the phase difference to be 0. Here in elliptical you do not need to consider the amplitude to be same, and phase can be plus minus pi by 2, right. So, this particular wave is called elliptically polarization or polarized, because you can see it is also giving the same kind of, it will trace a ellipse on this xy plane, because the two amplitudes are now not same and they differ by 90-degree phase, okay. So, here also you can get a left-handed or right-handed elliptical polarization, fine. So, equation wise, if you consider at z equal to 0, you can write Ax equals Ex will be equal to, that is your, the blue component will be equal to Ax cos omega t plus delta x, and Ey will be Ay cos omega t plus delta y, okay. And if you eliminate this time term, that is omega t, then you will find that Ex by Ax whole square plus Ey by Ay whole square minus 2 cos delta divided by Ax Ay times Ex Ey will be equal to sin square delta. So, this is basically the polarization ellipse equation, right, and that is why this electric field vector basically traces a ellipse on this xy plane. So, what we understood here is that a complete description of elliptical polarization will require these following things. First, the orientation of the ellipse, the shape of the ellipse, and the sense of rotation of the electric field vector, whether it is going clockwise or anti-clockwise. So, in general, the principal axes of the ellipse are not along the x and y axis, okay, it's typically like this, they are along x prime and y prime. So, you can rotate this coordinate system to the new axis, which is x prime and y prime, which is aligned with the major axis and minor axis of the ellipse, okay. In that case, you can write the equation of the ellipse in its standard form, that is Ex prime by a whole square plus Ey prime by b whole square will be equal to 1. So, here a is the length of the principal semi major axis, b is the length of the principal semi minor axis, and Ex prime and Ey prime are basically the field components in the rotated system. Now, So you are basically doing the frame transformation. So you are basically transforming between xy and x prime y prime frames. So how the electric fields will be related in these two frames, okay, because the rotation angle you consider to be phi, okay. So you can write Ex will be Ex prime or cos phi minus Ey prime sin phi, and Ey will be Ex prime sin phi plus Ey prime cos phi, okay. So this is basically a rotation in the same coordinate system, okay. So we will not go into the details of this. This is like something like the coordinate transformation, and if you consider, we are considering here phi as the rotation angle, that is basically the angle between the old x and the new x axis. So in that case, a square and b square, a is basically the half major axis, b is the half minor axis, they can be related to the earlier components like this. So a square will be ax square cos square phi plus ay square sin square phi plus ax ay cos delta sin 2 phi, and b square will have, you know, sin square in place of cos square here, cos square in place of sin square here, and this term remains same, just the sign will reverse. So this tilt angle of the ellipse can be given as tan 2 phi, which is basically 2 ax ay cos delta divided by ax square minus ay square. So once you know this orientation and the size of the polarization ellipse, okay, you can understand how the electric field vector is propagating, and to do so you require the knowledge of ax, ay and the phase difference delta between these two components. Now how do you determine the revolution direction of elliptical polarization? So you need to understand that the direction of rotation of the electric field vector basically depends on the sign of sin delta, okay. If sin delta is positive, the electric field basically rotates in a clockwise direction. If sin delta is negative, electric field rotates in counterclockwise direction. Now different values of phase difference delta can produce different shapes and orientation of the polarization ellipse. So the phase difference delta is very crucial because it controls both the shape of the ellipse and the sense of rotation, and you can define the ellipticity E of a polarization ellipse as E equals plus minus B by A, that is the ratio of the half mini axis divided by half major axis, okay. So here when you see positive sign in the ellipticity, this stands for right handed polarization, negative sign stands for left handed polarization. So now let us look into the polarization of light in anisotropic optical media, and it is very relevant to the liquid crystals as well, okay. So here we consider light propagation in a uniform non-magnetic anisotropic medium. So in an anisotropic medium, the speed of light basically depends on the direction of the electric field relative to the optical axis of that media. And how you define the optical property of any medium? You can use the dielectric tensor, which looks like this, epsilon in the tensor form. So you have this 3 by 3 matrix that basically gives you all the components. So if you have a non-absorbing medium, the dielectric tensor will have these properties, that epsilon ij will be equal to epsilon ji. That means they are real and symmetric. And when the tensor becomes symmetric, a special coordinate system called principal frame can be chosen for the analysis. So, or in the principal frame, you will see that the dielectric tensor basically becomes diagonal. It will have only 3 non-zero elements along the diagonal. One is epsilon x, the other one is epsilon y, and this one epsilon 3 is basically epsilon z. So this is epsilon 2, this is epsilon 1. So these basically represent the dielectric constant along the three principal axes. Now, if you use the Maxwell wave equation, we have seen earlier that you can take curl of E, you can write it as gradient of divergence of E minus del square E, then you substitute, this term becomes 0, okay, in the source free medium, and you get this, okay. So D can be further substituted using epsilon naught epsilon E. So this is how the wave equation looks like. So couple of important things to remember and recollect, you have discussed this earlier, that in an anisotropic medium, the D and E vector, the electric displacement and the electric field are not generally parallel. So the condition that del dot D equals del dot epsilon naught epsilon tensor E equals 0, this basically ensures that D is perpendicular to the propagation of the wave, that is the wave vector k. But this does not guarantee that E is also perpendicular to the propagation direction, that is k. So therefore, in an anisotropic medium, you can basically have some electric field along the direction of propagation. So this behavior is very different from what you have seen in the case of isotropic medium, where D and E, okay, both have orthogonal relationship with the wave propagation direction k. So how do you analyze the light propagation inside any anisotropic uniform medium? So when light propagates in such a medium, the direction of the electric field generally changes during its propagation. So if the electric field changes with propagation, that means the polarization state of light varies in space. However, for some special electric field directions, which are also called the eigenmodes, the polarization basically remain unchanged during the propagation. So these are the special directions which are called the normal modes or the eigenmodes. So how do you represent this? So in an eigenmode, the electric field can be written in this particular form, which you have seen earlier. Only difference here is that this is E naught, which is a constant vector called the eigenvector, okay. The corresponding refractive index seen by this wave will be called the eigenvalue, okay. So if you know the refractive index, you can always write the wave vector in this particular form, that is k equals 2 pi by lambda n into s cap, okay. So this whole thing can be written as k naught into n s cap. S cap is the direction of wave propagation, okay, or the Poynting vector. So this is basically the unit vector along the propagation direction, as you see it's mentioned here. So when you do this, you will get kx x cap plus ky y cap plus kz z cap. What is n? N is again the refractive index, which depends on the direction of propagation, direction of electric field, and also the anisotropic medium of the anisotropic properties of the medium. And here you can see there is k naught, which is basically 2 pi by lambda naught, which is the wave vector in free space. So now you can basically do some operator substitution and move to the frequency domain. So we have seen that for a monochromatic plane wave, if we write the electric field E equals E naught e to the power I omega t minus kr or k dot r, the partial time derivative can be replaced with I omega, and the spatial derivative delta can be replaced with minus I k. So if you substitute these relations into the Maxwell's wave equation, you get something like this: k dot E into k minus k square E will be equal to minus epsilon naught mu naught omega square epsilon, which is the tensor, times E, and this whole thing is basically your k naught square. So this becomes the fundamental equation that governs the eigenmode in an anisotropic medium. And you see the beauty of this equation, this basically relates the electric field vector, the wave vector, and the dielectric tensor, Okay. So, electric field vector, dielectric tensor is the material property, and the wave vector tells you the wave propagation direction. So, all these things become related here. If you want to use matrix form of this eigenvalue equation, it allows you to write the dielectric tensor in the diagonal form as we have seen. So, you put this back into the equation we have seen earlier, you get the wave equation in this particular form. So, this is again the wave equation, but it is in a matrix form and it is valid for anisotropic medium. So, what can be the non-trivial solution condition here? So, for a non-zero electric field solution, the determinant of this matrix must be 0. Okay. So, this becomes, so this is the determinant of the matrix in this A is equal to 0, A is the equation number. So, this is the eigen equation and it basically determines the allowed refractive indices that can support a given propagation direction. So, now let us do the variable substitution. So, we can define the principal refractive indices, okay, as nx square will be equal to Ex epsilon x, and y square will be equal to epsilon y, and nz square will be equal to epsilon z. Again, we consider here one assumption that this material is non-absorbing. Okay. So, with that you can write the normalized wave vector components Ax to be equal to kx by k naught whole square, which is nothing but n sx whole square. Ay will be ky by kx k naught whole square, that is equal to n sy whole square. Az will be equal to kz by k naught whole square, that is n sz whole square. So, we already know what is nx, ny, nz are. They are the refractive index along the three principal axes. Similarly, ax, ay, az are also the squared direction cosines multiplied by the n square. Okay. And n here refers to the refractive index for the eigenmode. Okay. So, Sx, Sy and Sz are also the components of the unit vector S cap. So, if you take square of these components and add up, you will get 1. So, this can be used in this equation also, and you can write A equals Ax plus Ay plus Az, that will be equal to n square. So, if you expand the determinant of the equation A and B, and if you simplify, this is what you get: n square minus nx square into n square minus ny square into n square minus nz square will be equal to this. Okay. So, this is the eigen equation. So, now let us look into the Fresnel equation of the wave normals. So, once you simplify that large equation, you can actually get the refractive index relations from the eigen equation that you have seen. So, in the previous equation, here you can consider the case when n square minus nx square is non-zero, n square minus ny square is non-zero, and n square minus nz square is also non-zero. Okay. In that case, the equation C can be rewritten in a simpler form, which looks like sx square divided by n square minus nx square plus sy square divided by n square minus ny square plus sz square divided by n square minus nz square will be equal to 1 by n square. So, this is the equation which is known as the Fresnel equation of wave normals. Now, you can use this to calculate the refractive indices of these eigenmodes. So, what are the key properties of this Fresnel equation? So, you can see that this is basically quadratic in n square. That means it will give you two solution of n. Okay. N will be greater than 0. Okay. And for a given propagation direction, these two refractive indices will basically correspond to two eigenmodes. Okay. So, simpler than this one is much simpler to use than the earlier larger eigen equation. but here this particular condition needs to be satisfied. What is this condition that you can write in generic form? It is n square minus ni square should not be equal to 0. Now, if in any case n is becoming equal to ni, then you will get wrong answers. So, you got to be very careful about that. So, this eigen electric field, this can be expressed in terms of the propagation direction and the principal refractive indices. As you see here, the eigen field vector can be written in terms of this. These are basically the components, right? And this equation basically gives the direction of the electric field for a particular eigenmode. Therefore, the eigenmode is basically linearly polarized in a uniform anisotropic medium. And if you want to know the exact direction, you need to know Sx, Sy and Sz, the three components of the unit vector of the propagation direction. That means you need to know the propagation direction. You need to know the principal refractive indices, that is Nx, Ny and Nz, and also you need to know the eigen value n. Okay, then you can determine this particular eigenmodes. Okay. So, we are talking about this eigenmodes of the eigen electric field vector, but what is the physical meaning of this eigenmodes? So, let us try to understand that. So, for a given propagation direction, if the input polarization matches an eigenmode, then what will happen? The electric field direction will not change. The polarization will remain invariant and the wave will be able to propagate with the velocity given by c by n. So, n is basically the corresponding eigen refractive index. Now, if the input polarization does not match along or is not along the eigenmode, so what you can do, the input polarization can be then decomposed into two eigenmode components, and these two eigenmode components will basically propagate independently. And because they will have now different refractive indices, they will also now travel at different phase velocities. So, what will happen after propagation over a certain distance, their resulting propagation, when you add up those two components, the effective polarization will be different than the incident or the starting polarization. So, here the resultant polarization basically changes with distance. So, that brings us to a beautiful concept called refractive index ellipsoid, which allows visualization of these eigen refractive indices and the eigen vectors. Okay. So, this is how a refractive index ellipsoid looks like. The major axes of the ellipsoid are basically parallel to the x, y and z. Okay. So, this is x, this is y and this is z. And what is the length? The axis length are typically 2nx, 2ny and 2nz. So, you can write the refractive index ellipsoid equation to be x square divided by nx square plus y square divided by ny square plus z square divided by nz square equal 1. So, this ellipsoid basically allows you to visualize how refractive index changes, or it depends on different direction, because in different direction you will have different refractive index. Okay, and that is how the case is in anisotropic medium. Now, if you draw a line through the origin, and one important thing is that this is where your S bar is, or S cap is drawn. So, if you basically draw a line through the origin which is parallel to this S cap, and it will basically cut a plane, okay, through the origin which is perpendicular to this particular S cap direction. So, this is that plane. So, in that case what you can write, so the vectors along S cap, they will now add up to 0. So, S cap times x cap plus y cap plus z cap will give you Sx x plus Syy plus Sz z. So, this is how in this particular plane you can find what are the components, and that will be equal to 0. And whenever you try to take intersection of this plane with this ellipsoid that is being formed, you basically get an ellipse, and the distance of any point on this ellipse from the origin will be the refractive index, that is n, which will be given by square root of x square plus y square plus z square. Okay. So, with that we conclude our discussion here. If you have got any doubt regarding this lecture, you can drop an email to this email address mentioning the course name on the subject line. Thank you.